They have the helpful voice of Zoom. Okay, well, this week we're very happy to have Stephen Taylor from Vanderbilt, who is a member of the NANOGrav collaboration, here to talk a bit to us about some of their recent results. So, Stephen.
Thank you very much. I really appreciate this opportunity to come and talk to you all today about these new results. As Robert mentioned, I'm in the NANOGrav collaboration. I'm actually a chair of the detection working group out of which this paper came, and in the NANOGrav management team as well. So I can give a big overview of the kind of science that we do, as well as these specific results. So I will give an overview of the gravitational wave landscape and some introductory material on how we actually go about trying to detect gravitational waves with pulsar timing arrays, before then going on to the primary sources we expect to be seen in this band of nanohertz frequencies, and that's supermassive binary black holes. Then I'll discuss the state-of-the-art results that we've produced from the collaboration, and then what they might mean. So I'll give some context for what they might mean if they do happen to indicate early signs of gravitational wave signals. And then I'll finish off, if I have time, on what I think the future of multi-messenger astronomy could be in this particular band of gravitational wave discovery. All right, so you might have seen an image like this before. This is showing the gravitational wave landscape as a function of the characteristic strain, effectively the loudness of the gravitational waves, and the frequency, the observed frequency of the gravitational waves. And the gravitational waves that have been discovered so far directly come from the LIGO-Virgo collaboration. They're discoveries of stellar mass binary black holes, neutron star collisions, possibly neutron star black hole collisions, and this new discovery of an intermediate mass black hole system that's of the order 100 solar masses. But by and large, these are systems of black holes that are of order stellar masses, so tens to maybe 100 solar masses. If we want to explore more parts of the black hole sort of zoo, then we need to go lower in frequency. So if you want to see larger black holes, you need to go lower in gravitational wave frequency. And that takes us to the LISA detector that we will hopefully have operational in the mid-2030s. LISA is the Laser Interferometer Space Antenna. It's due for launch in 2034. It's primarily an ESA mission, but we'll have a big contribution from NASA as well. It's a really international mission. And within the LISA band of millihertz gravitational wave frequencies, we expect to see massive black hole binary systems that are of order 10 to the 4 to 10 to the 7 solar masses colliding with each other. And we should also have lots of other interesting types of systems. For example, extreme mass ratio inspirals, where one black hole is gigantic, and then we also have a much smaller compact object that effectively acts as a test mass within the metric of the larger black hole. And so these smaller masses tracing out the space-time and allowing for very precision tests of the structure of space-time around this black hole. So LISA will be an extraordinary detector to do precision tests of GR and modified theories of GR. If we want to go to the most massive black holes in the universe, then we need to go to the pulsar timing array band, where we're down at nanohertz up to hundreds of nanohertz in frequency. And so the kinds of black holes that are languishing in this band are 10 to the 7 to 10 to the 10 solar masses. So these are the kinds of black holes that are occupying the centers of the most massive galaxies in the universe. And what we're seeing here is a representation of the sensitivity curve of what NANOGrav attained in 2018. This was from NANOGrav's analysis of 11 years of data, 11 years of precision pulsar timing data from 34 pulsars. And then below that is a projection of where the International Pulsar Timing Array sensitivity could be in the early to mid 2020s. And I'll discuss what the IPTA is in a little bit of time. So you're also seeing the sources that are in this nanohertz band. We've got individual supermassive black hole binaries that could stick up above the level of a stochastic background formed from the entire aggregate of all of these signals from supermassive black hole binaries. So in PTA space, we actually expect the stochastic background from lots and lots of supermassive black hole binaries will be detected first. And then once we reach enough sensitivity and detection significance, the individual loud binaries that are making up that background will be able to stick up above the level of the background enough that we can resolve them individually. So having explained the broad concept, let me talk about pulsars and how we go about this detection process with pulsar timing arrays. Over long observational campaigns, we can time pulsars incredibly well and build up very sophisticated models of when we expect the pulses to arrive. And the models will be a function of the spin period of the pulsar, how fast it's spinning down. It's a rotationally powered object, and as it emits electromagnetic radiation, it is spinning down. Some other parts of the timing model that describe the arrival times of the pulses will be its position in the sky, and also propagation effects as the radio pulses are moving through the ionized interstellar medium on their way to the Earth. So lower radio frequencies in the pulse will arrive later than the higher radio frequencies. So these are very sophisticated models that we can construct, but what they don't take into account at leading order is the influence of a gravitational wave signal. A gravitational wave signal that's coming from outside of our galaxy and sort of transiting this Earth pulsar line of sight will change the proper separation of the Earth and pulsar system. And this will cause the pulses to either arrive earlier or later than expected. So we get these perturbations to the arrival times as an influence of a gravitational wave moving between the Earth and the pulsar. So this is an exciting prospect. We can use these Earth pulsar lines of sight and precision timing to hunt for low frequency gravitational waves. Unfortunately, what we have is that the signals we're looking for are quite low frequency themselves. And there are intrinsic noise processes within the pulsars that can masquerade as the kind of gravitational waves we're looking for. So if we were just looking at a single pulsar and we were timing it over a long period of time, then we would never be able to confidently separate the intrinsic noise within that pulsar from a possible gravitational wave signal. And so we don't just rely on one pulsar, we perform precision timing of an array of pulsars. So we imagine ourselves to be like a spider in the midst of this big galactic web, where each leg of the spider and each part of the strand of the web is an Earth pulsar system. And what we look for are correlated tinglings within that web. We're looking for correlated timing delays caused by gravitational waves moving through the entire system of pulsars. And it's not just NANOGrav that's trying this. NANOGrav is the North American Nanohertz Observatory for Gravitational Waves. That's the collaboration that I work most closely with. And we use the Green Bank Observatory in West Virginia. We also use the Arecibo Radio Telescope in Puerto Rico. We're also making some test observations with the VLA and possibly CHIME as well in Canada. But there are several other pulsar timing array collaborations. This is only a small collection of the telescopes that the European Pulsar Timing Array has access to. There's also the Parkes Pulsar Timing Array, which uses the Parkes Radio Telescope in Australia. And in addition to that, we have new collaborations and new colleagues that are joining us in South Africa, possibly using Meerkat and in the future, the Square Kilometre Array. There's also the Indian Pulsar Timing Array that has just started operations, and then potentially the Chinese Pulsar Timing Array, which could use a sequence of radio telescopes, but certainly FAST, the 500-meter aperture spherical telescope, is a great survey telescope for finding new pulsars. Possibly not for precision timing, but as a survey telescope, it's fantastic. And our goal is to work all together within the combined efforts of the International Pulsar Timing Array. So NANOGrav is just like the ePTA and the PPTA and these other collaborations are part of the International Pulsar Timing Array. And our ultimate goal is to get to gravitational wave science faster by fusing our data sets together and really making this a joint international effort. All right, so that's the broad idea of how we detect gravitational waves with precision pulsar timing. Let me now discuss what we expect within this band that PTAs are accessible to. The frequencies that we can access of the gravitational wave spectrum with pulsar timing arrays are set by how we sample the time series of the arrival times of the pulses. We're typically observing these millisecond pulsars over years to decades timescales. So the lowest frequency we can access in a Fourier sense is roughly 1 over the observation time. So if we've got about 15 years of observations, then that means we can probe gravitational wave frequencies down to about 2 nanohertz. Then the highest frequency is set by how often we observe the pulsars. We typically are observing a pulsar for about 30 minutes within a given observing session, and then that's fusing together lots and lots of pulses to give us a single observation. We then go back to that pulsar after a few weeks. So our cadence between observations is a few weeks, and that's fine because we're only interested in lower frequency gravitational waves. So we can probe up to about the Nyquist sampling frequency of a few hundred nanohertz with that kind of observational cadence. Now, within this band of sensitivity, we expect there should be lots and lots of supermassive black hole binary signals waiting for us. We expect that supermassive binary black hole systems should form naturally as a byproduct of hierarchical galaxy growth, where smaller galaxies are merging over cosmic time to form larger galaxies. And we know that most massive galaxies contain a resonant supermassive black hole at their center. There are lots of well-known scaling relationships that link the mass of the black hole at the center to the mass of the galaxy itself, or properties of the galaxy. And so we expect that over cosmic time, lots and lots of galaxies are merging together, forming binary systems that are emitting gravitational waves. So these systems should be forming naturally within our picture of galaxy growth. Now, this is showing how we expect these gravitational wave signals from the supermassive black hole binaries to manifest in our pulsar timing array spectrum. As I mentioned before, the resolution of our pulsar timing array is not quite good enough to individually resolve every single supermassive black hole binary. And that's really because within the pulsar timing array band, the waveform, the gravitational waveform, is almost sinusoidal. Unlike LIGO, we're not going to see significant evolution of the frequency of the system, nor are we going to be able to see the actual merger of the binary system itself. LIGO sees the whole process, the late-in spiral, the merger, and then some aspects of the ring-down behavior as well of the black hole, combined black hole. But what we see are the systems at the very early adiabatic in-spiral stage. So the frequency evolution is almost negligible. And the time to coalescence of anything we see in the PTA band could be mega years. So to a good approximation, we're dealing with sinusoidal signals, and our signals are present in our entire data stream. So these signals are there right now in our data set, waiting for us to observe longer and waiting to build in significance. So we can't resolve all of these signals individually. They tend to build up as a confusion background that we hunt statistically as a stochastic gravitational wave background. So that's what we expect to be able to detect first. And then as time goes on, we should be able to pick out individual sources that are particularly nearby or massive, that they are sticking up above the level of this background. So once we have these single sources, we can start characterizing their binary orbits and other properties, just like LIGO does and what LISA will do in the future. Now, on the right-hand side of this plot, there's another aspect of the merger that I want to talk about, and that's the gravitational wave memory. So the gravitational wave memory is almost a little offset, a step function offset in the metric that occurs after the merger has taken place. So the space-time metric does not just go back to what it was before. There's a little DC offset in that, and that's the gravitational wave memory. It's a permanent imprint of the merger that appears in the waveform. And this kind of offset in the metric appears in timing delays as a ramp. So we have to, in order to convert any gravitational wave strain signal into the induced timing delays in our pulsars, we have to integrate over time. So integrating over a step function gives us a ramp, and we should expect to see a ramp in our time series. This kind of ramp is very low frequency, and we should be able to isolate that kind of memory burst that way. So we're not going to be sensitive to the oscillatory components of the binary merger, but we should be indirectly sensitive to the binary merger through the memory offset that it creates. All right, so I've talked about how we will get supermassive black hole binary signals in this band and how pulsar timing arrays should be sensitive to individual signals. What I'd like to talk about now is how we'll actually detect the stochastic background of gravitational waves from the entire aggregation of all of these signals coming from all across cosmic time. So we're probing this stochastic gravitational wave background as just through statistical means. We're looking at correlations, low frequency correlations between pairs of pulsars across the sky. And that means that when we eventually claim detection of stochastic background, it'll be based on a very specific correlation signature that we expect to exist between the pulsars, between the timing delays in the pulsars. And that correlation signature is called the Hellions and Downs curve. It's a very well-known correlation signature applicable to an isotropic stochastic gravitational wave background. It's quadrupolar in its correlation signature. That means that if we did some sort of decomposition in Legendre polynomials, then we get a big peak at L equals 2. We shouldn't have anything in the monopole of the dipole from this curve. We would get diminishing power in higher multipoles beyond L equals 2. And I'll show that later on in this talk. The purpose of showing this slide is to say that if we want to trace out this correlation signature, then we need to time lots and lots of pulsars. We don't really want the few best pulsars, the few best timed pulsars in the night sky. We care more about having lots and lots of pulsars in order to forge these correlation pairs. So the more pairs we get, the more we're able to trace out what we have here, which is the Hellions and Downs correlation signature. And the correlation signature is showing the correlation in these arrival time delays between pulsars that are separated by certain angles across the sky. And what's great is that this correlation signature is only a function of the angular separation of the pulsars on the sky. Now, there are other kinds of spatially correlated.
Sorry, just to ask a quick question.
Sure. Yeah.
So this is saying that as we take the angular separation down to 0, we don't have a perfect correlation between these things. So this is assuming some kind of independent noise on each pulsar.
Yes, yeah, let me clarify what happens down at low angular separation. That's a really good question. You're not seeing it here, but there is a really rapid jump from 0.5 up to 1.0. So if we're dealing with the same pulsar and we're correlating with itself, then certainly it has a correlation of 1. But as we separate the pulsars on the sky even a little bit, that drops towards 0.5. And that's really because only half of the gravitational wave signal is correlated. As a gravitational wave transits the Earth pulsar line of sight, we get an imprint of the gravitational waveform at the pulsar. So we get an imprint of the metric perturbation at the pulsar, and then we get an imprint of the metric perturbation at the Earth. It turns out that everything else in between, the metric perturbation in between, just integrates out to 0. So to a good approximation, the signal is a combination of the metric perturbation at the Earth and the metric perturbation of the pulsar. Now, the Earth term is completely common to all of the pulsars, so that's completely correlated. But the other half of the signal is not correlated. That's the pulsar term, and that's an imprint of the metric perturbation whenever the gravitational wave passed by those pulsars. And those are happening at different times. So the other half of this signal is not correlated. That's why it seems to drop very suddenly to 0.5.
Okay, so that's based on the fact that pulsars are at different distances from us, even if on the same line of sight. Okay, cool, thanks.
Can you say some more about this curve? Like, for example, why at diametrically opposite points at 180 degrees does it not go back to 0.5? I would have thought that in that case, like, also the Earth term is exactly correlated. And similarly, why is the dip? The dip is not at exactly 90 degrees. I would expect that probably for a quadrupolar signal, the lowest correlation would be at 90 degrees. And in fact, there's anti-correlation. So yeah.
Right. Yeah, it's it's mostly quadrupolar. But I will show later that there are higher multipoles that are kind of skewing this off from being from going back to 0.5 and falling to a minimum at exactly 90 degrees. So the individual antenna response patterns of each pulsar are perfectly quadrupolar. But then when we overlap them and get this kind of correlation signature between them, for an isotropic background, that actually creates something that's mostly quadrupolar. You get a huge peak, but then there are these higher multipoles as well. And it's the higher multipoles that are skewing this from your expectations of going back to 0.5 and being a minimum of 90. Okay, there are some other pesky noise processes that can induce spatially correlated signatures. And those might include global time standard errors. So if we have a global time standard that we're referencing all of our pulsars to, then that will be shared in all of the pulsars. There'll be a low frequency drift in all of the pulsars from our per baselining to a global time standard. And that will look like a monopole correlated error in all the pulsars. Effectively, it will look like a horizontal line on this diagram. And as I'll talk about in a little bit, any errors in how we reference our observations back to the barycenter of the solar system, which is something we do, can induce dipole correlated errors. So it look like a cosine in this diagram. And we reference our observations back to the barycenter because it acts as a quasi-inertial reference frame for our observations. So let me now get to some of these state-of-the-art results, including the NANOGrav 12.5-year results. As I mentioned just a minute ago, we do reference our observations back to the solar system barycenter, and that's part of a chain of timing corrections that we do in this diagram in the top left. You take your observed time of arrival at a radio telescope, you correct that to the geocenter, you correct that back to the solar system barycenter, and then to the emitting system. Now the correction from the geocenter to the solar system barycenter is just the Romer delay. That's classical light travel time across the solar system. And we need to know the position of the barycenter in order to do that Romer delay to within a 100-meter accuracy in order to be able to detect gravitational waves. 100-meter accuracy translates to roughly 100 nanosecond accuracy in the Romer delay. This is quite a demanding use case for models of the solar system barycenter. There are a few sources of the solar system barycenter position, one of which is the Jet Propulsion Laboratory, which produces a solar system ephemeris every couple of years based on updated spacecraft data and updated fits to all of the important dynamical objects in the solar system. But for us, for pulsar timing arrays, the most important object by and large is Jupiter, because the solar system roughly is a binary system with the sun and Jupiter. What you're seeing here are some results from the NANOGrav 11-year analysis. This was just from about 2 years ago, where we discovered this systematic error coming from solar system ephemeris issues. The solar system ephemeris that is provided by JPL and other collaborations like INPOP in France is a point estimate of the trajectories of the dynamical objects in the solar system. And they don't really provide an error spread or an error budget for the analysis. It's just not part of how the fitting procedure is done there. So when we take that as given and compute the Romer delay, we get constraints on the gravitational wave background from our analysis that are beholden to the particular version of the JPL model that we used to compute the Romer delays. What you're seeing here is the posterior probability distribution of the amplitude of a stochastic gravitational wave background in this spectral model that goes as A times F to the minus 2/3. That kind of spectrum is what we would expect from a population of in-spiral and supermassive black hole binaries. So this is our posterior distribution. This is our belief spread in the amplitude of this background. And the different curves correspond to different versions of the JPL model of the solar system. And we get different answers depending on which one we use. And it's not always the case that the newer one is the better one, because there's no monotonic upwards or downwards trend in the way these curves are going as the version of the ephemeris increases in time. So this is very unsatisfying, because if we take a rough estimate of the Bayesian odds of this amplitude of this process in our data, just based on an estimate of the Savage-Dickey density ratio, which is related to the inverse of this probability density in the lowest bin of this histogram, you would get an answer of the Bayes factor, the Bayesian odds, roughly, that varies by over an order of magnitude. So this is very unsatisfying that we should get such a different answer depending on which version of the ephemeris we use. And so what we did was we acted like good Bayesians and decided to marginalize over these uncertainties ourselves. So we built what we call Bayes-FM. It's the first Bayesian solar system ephemeris model, and it makes perturbative corrections to Jupiter's orbit, along with corrections to the masses of the gas giants. And it's doing all this simultaneously with our searches for the gravitational wave background. Once we do that, once we apply these small perturbations and marginalize over those perturbations, we get to a common answer, regardless of which baseline ephemeris we started from. So all of these curves just collapse together very nicely, and we get a common answer. So this was a big breakthrough a few years ago. The solar system ephemeris turned out to be a source of systematic uncertainty for us. But now we believe that with this modeling strategy and even newer versions of the ephemeris, that we're able to plow through this noise floor, and it shouldn't be a problem anymore. So this now brings me to the NANOGrav 12.5-year data set, our most recent analysis. It was actually led by a colleague of mine, along with all of us in the detection working group, Joe Simon, who was formerly at JPL, where we were colleagues, and is now a postdoc at CU Boulder. What we're seeing in an analysis of this data set is it's not an upper limit on this kind of stochastic process anymore. We seem to be seeing a very steep spectrum common process across a large fraction of our 45 pulsar array. And the maximum baseline of this array is about 12.9 years, which gets us to roughly 2 nanohertz, thereabouts, the lowest frequency. On the left-hand side here, you're seeing effectively a periodogram measuring this steep spectrum process from all of the pulsars in the array, and that's shown by the kind of violin shapes in gray. And the lowest free frequencies, about up to 5, are well constrained as a very steep spectrum process. At higher frequencies, if we incorporate them in the search, then excess white noise contamination is really tilting a fit of a power law to something much shallower. So we expect that since the gravitational wave background is only affecting the lower frequencies, or it should only be affecting the lower frequencies, that we can apply a more adaptive model that flattens out the spectrum at higher frequencies due to contamination. So we effectively fit and marginalize over any contamination from higher frequencies through this blue adaptive curve on the left here. That's simply confirming that the lowest 5 frequencies are well fit to a steep power law behavior, which is what you're seeing again in the orange dashed line. This kind of steep spectrum process amplitude is shown in its probability density form on the right-hand side. So you're seeing in blue and orange the probability density of the amplitude of this common spectrum process with different versions of the JPL ephemeris and the INPOP French ephemeris. Here, it doesn't seem to be making a difference which version of the ephemeris we use. It's unable to impact us too much. We now seem to be data dominated, so the ephemeris is not causing us too many issues now that we've gone deeper into frequency space. The median amplitude of this common spectrum process is about 2 × 10⁻15. And if we apply our Bayes-FM model, then yes, it does seem to diminish the amplitude a little bit, but it's well within the posterior spread. So there is some covariance of our Bayes FM modeling with this common spectrum process, but it's well within the spread.
Sorry, just to
sorry.
Okay.
Sure.
Robert, you can go.
No, go for it.
On the right plot, this is only a fit to the amplitude of the broken power law, like the yellow dashed line on the left-hand side?
Yes, that's right.
Okay.
So yeah, you were saying that this is the fit to a common spectrum process. Is this driven pretty equally by all of your 45 pulsars, or is it sort of most of the signal to noise that's coming from some subset of them?
That's a great question. It's actually my next slide, talking about the contributions from each pulsar. Sure. Yeah, so we can compute a statistic that we call the dropout factor. It's essentially the leave one out cross-validation probability. So if we leave pulsars out of the fit, then how much is their data supporting the common process that is found in the rest of the data? What we find is that about a third of the pulsars are in support of this common process. That translates into this plot of a dropout factor that's greater than 1. Then a large swathe of them are ambivalent towards this process. And then there are some pulsars that are interestingly not in support of this common process across the pulsars. And the most interesting one that doesn't support this common process is a pulsar known as J1713 plus 0747. It's actually one of our best, highest quality timed pulsars. Now we think it's not supporting this common process because of a transient feature in its time series that is very close to the end of our data set. This transient feature, we think, is it's a void in the interstellar medium that leads to what seems like a dip in the time series. So there is some sort of transient chromatic feature, radio frequency dependent feature that's impacting the end of the data set. Now, if we just decide to chop off the end of the data set from this pulsar and replace it with its 11-year data set, so we chop off about the last year and a half that has this transient feature in it, then it becomes in support of this common process. So this is one of the tests that we decided to do to understand why one of our best pulsars was not supporting this. Yeah, and Robert, to answer your question, it's about a third of the best ones that are well in support of this common process. A large selection of the other ones are sort of ambivalent, and then only a few are not even that disfavored by this process.
Okay, cool, that's useful. So if you say, presumably you've run simulations of what would happen if you had a gravitational wave thing, is this approximately what you'd see for a sort of injected signal? Is this what you'd expect? Yes, it is what we would expect from an injected signal, apart from this kind of behavior at the right-hand side. Okay. So we haven't fully explored the impact of mismodeling on these dropout factors. We would expect that pulsars would, in our simulations, we have seen that most pulsars will start around 1 and then they'll just rise up to the left-hand side and increase. We need to explore more the impact of mismodeling, but it does seem that the mismodeling of this transient feature is causing this dip to lower values below 1. Okay, thanks. Sure.
Does the dropout analysis of J1713 for 11 years also support this?
Yes, I should have pointed this out explicitly. That's what the green sort of hollow circle is on the very right-hand side. So if you go to the very right-hand side of this plot, the last pulsar corresponds to 1713. And in the 12.5-year data set, it has a dropout that's below 1. That's the filled green circle at the very right-hand edge of this plot. Now, replacing that by just the 11-year version, by chopping off a year and a half, gets us above 1 to this hollow green circle that's above.
Sorry, what do the blue dots correspond to?
The blue dots are just a different way of getting to this cross-validation probability.
I see. I was wondering if the blue and orange also support the same movement with the 11-year data set?
Yeah, the blue and the orange is when we do this dropout analysis, when we include BASE-FM, the Bayesian ephemeris marginalization in the analysis, and that kind of diminishes a little bit of the dropout significance because it's slightly covariant with the signals we're searching for. It's fitting perturbations to Jupiter's orbit. Jupiter has a period of roughly 11.9 years, and so the processes are covariant. But yes, we're still seeing that the best pulsars, most of the best pulsars, are favoring this common process.
Thank you. Also,
Sure.
is there anything special about the position of the pulsars in the sky of the first bunch which show this common spectrum process?
There's nothing particularly special about their position on the sky. All of these pulsars that are shown here are reflecting NANOGrav's sensitivity using the telescopes it has. So these are primarily northern hemisphere pulsars. But we have ongoing experiments and tests with the International Pulsar Timing Array, which gives us access to the southern hemisphere.
Thank you.
Sure. Now I've talked about this common spectrum process, which is something that's spectrally similar in the pulsars, but really the smoking gun evidence that we need to claim detection of the stochastic background is this signature in the cross correlations between the pulsars. We have various frequentist statistics and Bayesian analyses that can recover this. In the top left, you're seeing a frequentist estimator of these cross correlations in our 11-year data set. This appears to be a lot of scatter around 0. But in 12.5 years, in the bottom left, the error bars are getting tighter. Again, we don't have much significance in these cross correlations yet. The same is true in the Bayesian analysis, where everything is pretty much consistent with 0 correlations. When we compute the Bayesian odds for the Hellions and Downs correlations between the pulsars, then we get an odds ratio of about 2 to 4 in favor of these correlations. So that's nothing to write home about, not very significant at all. The one thing we can do to see if this grows is to increase the number of pulsars and also time for much longer.
So just to ask a similar question on this, if we'd have put in, say, some injected signal, which was a gravitational wave with quadrupolar correlations, how big an odds ratio should we have got?
Yeah, that's a very good question, and it actually goes on to a couple of slides' time.
Okay.
So we would expect that if there were an amplitude similar to what we've seen of the gravitational wave background in our data set, then the results that we're getting so far are consistent with our expectations.
Okay.
We would expect that there would be this common spectrum process that emerges first, and then as the cross correlation information gets stronger, that starts to grow very, very quickly. So there is a time lag between the emergence of a common spectrum process and the definitive evidence for the cross correlations.
Okay, thanks.
And we have various ways of testing the significance of the cross correlations we see in our data. We have a different procedure from what LIGO Virgo does because they're dealing with very short timescale transient signals. We have signals that permeate the entire data stream, so we have to have different methods. We just have methods that effectively break any possible cross correlations that exist in our real data set, so we can map out the null distribution of our detection statistics. So at the moment, we expect that our p-value for what we see is about 5 to 10%. So not very significant in the cross correlations yet, but very significant in the common spectrum process. So again, we just need to wait for longer and see if the evidence of the cross correlation grows with time. All right, so let me get on to the last few minutes. Robert, how much time would I have left?
Sorry, I was muted. Yeah, feel free to go up till 3, that's fine.
Perfect, thank you. So given the results from the NANOGrav collaboration that I've shown, we decided to undertake a suite of forecasting studies and say, all right, imagine that this is the gravitational wave background that happens to be in our data set. We don't know for sure yet, but what should we expect to see in the future? And can we establish some milestones for the future to guide us all? So this is showing timeline to detection, which is certainly one interesting metric for us to look at. What I'm going to show next, though, really is time to science. We want to not just say when can we detect the background or when can we detect a single source, but when can we start to characterize the background and extract some interest in astrophysics from it. Now, based on some previous simulations, we expect that the stochastic background will emerge in our data and be detectable within the next few years at the latest. And especially if this happens to be the first signs of that background in our data. Then as time goes on, we expect the stochastic background to be more well characterized, and therefore it's easier for us to extract single resolvable binary signals from within that background. So we expect to be able to do that by the end of this decade. So this study that involves lots of forecasting into the future is being led by my postdoc, Dr. Nihan Paul at Vanderbilt. And what we've done is effectively taken the NANOGrav 12.5-year data set, emulated its sensitivity, and then projected that into the future, so that instead of 12.5 years, we collect up to 20 years of data. We don't add new pulsars, which makes everything that I show here very conservative, because we're adding pulsars at a rate of about 4 per year, and more pulsars gets us to detection faster. But even in these few select panels that I'm showing here, which are realization averaged recoveries of the cross correlations, once we get up to about 15 years, we're able to get to a Hellings's and Downs cross correlation signal to noise ratio of about 5. So even though we have a lower detection significance in the cross correlations right now, as we add just a few more years of data, we should be in the regime where we should start to expect to see a stochastic gravitational wave background. There are 2 different metrics shown on here I should explain. Robert, did you have a question before I do that?
Oh, sorry, just briefly. How much does this assume about the intrinsic noise variability of pulsars? Are you making some assumption that we might discover new pulsar physics that means they're actually noisier than we thought? Could that mess with this or not?
Given the frequency of the signals we're probing, we don't expect that this amount of time will reveal new features in the spectrum of the noise that muddy the waters here. We're taking the real noise properties that have been measured, and we're making data sets that reflect the real noise properties that have been measured.
Okay, cool.
And same question, but for like the interstellar medium, like this seemed to be the problem with one of the pulsars.
Right. Yes. So the interstellar medium is not something we've thoroughly studied here. So again, this is a conservative estimate, assuming that we can characterize the interstellar medium and model these transient features well. We do have ongoing efforts to have custom noise modeling for each pulsar that can mitigate this kind of issue. So at the moment, we model all of the pulsars with the same sort of vanilla modeling strategy. We give it a low frequency intrinsic noise. We allow there to be also some chromatic variations due to dispersion measure. But in the future, we do need to model each pulsar on an individual basis and account for sort of the idiosyncrasies in each pulsar. Provided we can do that, then we don't expect it's a problem, because we characterize the observations over lots of radio frequencies, allowing us to isolate dispersion measure variations from other noise.
Thank you.
All right, so in this plot here, you're seeing 2 detection statistics, 2 rows. There's row hat, which is the total signal to noise ratio. That's the signal to noise from all of the gravitational wave background and how it affects all of the pulsars, including the autocorrelations of each pulsar with itself. Row HD is just the cross correlations, just the distinct cross pairings of pulsars with other pulsars. And that's really the metric we look at when claiming detection significance, or when trying to claim a detection. Row hat is what we characterize our scientific outcomes in terms of, because that includes all of the information in the likelihood and helps us quantify when we would expect to be able to measure the background and its properties well. Once we start to detect the gravitational wave background, we can start to probe the multipolar structure of these cross correlations. On the lower left here, you're seeing something I've alluded to, and that's the decomposition of the cross correlations in terms of multipoles and how well we're able to characterize the multipolar coefficients as time goes on. We expect that the Hellings's and Downs curve should have almost no overlap with monopole and dipole polynomials. A big peak in the quadrupole, and then we get a slow tail off into higher multipoles. So our goal is to measure this and to really isolate this kind of cross-correlation signature for many possible monopole and dipole signatures. And in the top right, you're seeing a figure that is actually in our paper on this forecast project, and that's showing how as time goes on, even though there's overlap in the cross-correlation signal-to-noise ratio of monopole, dipole, and gravitational wave background signals, that overlap very quickly diminishes as the true signal-to-noise wins out. So there's always going to be some overlap from noise and from noise fluctuations in the low signal-to-noise regime, but then as time goes on, the true signal template wins out. Now, one of the very interesting things that came out of our project was being able to characterize when we can start to constrain and measure the amplitude of the stochastic background and also the spectral index of that stochastic background. What you're seeing here is the fractional uncertainty on those parameters as a function of the total signal-to-noise ratio. And in contrast on this is where we are in the NANOGrav 12.5-year data set so far. So we're falling on this curve of expectations at the moment. We don't have significance in the cross correlations, but we are following expectations for scientific outcomes, measuring the amplitude and the spectral index if this happens to be a real signal. Or we can translate the signal-to-noise ratio rho hat into factors that influence the significance, like the total time of observation of the pulsars, the number of pulsars, the time and quality. So really these kinds of scaling relationships here are fully generalizable to any other PTA configuration or noise characteristics. So we expect right around the time of initial detection of the background that we'll have a 44% uncertainty on the amplitude of the background and a 40% uncertainty on the spectral index. And getting a good measure of the spectral index tells us how we can separate the origin of this background from different types of origin. So we expect it will be supermassive black hole binaries, but measuring the spectral index alpha well allows us to discriminate and discredit other origins that are more exotic, like cosmic strings or primordial gravitational waves. Once we go beyond characterization of simply a power law for the strain spectrum, we can look at how we can use the amplitude to give us information about the merger rate of massive black holes and inform current models of host galaxy black hole relationships like the M bulge relationship or the M sigma relationship. Another interesting prospect shown in this blue curve on this diagram is as we go to lower frequencies, we're looking at a population of black holes that are at wider and wider separations. And at those wide separations, they might actually still be in contact with their external galactic environment. So they might still be being driven and influenced by interactions with stars or interactions with a circumbinary gaseous disk. So the position of a turnover in the spectrum and the gradient of the turnover at lower frequencies actually gives us quite a lot of astrophysical information and allows us to say something about how black holes evolve through the final parsec of their dynamical evolution. So this work is, it should appear on arXiv this coming Monday. It's called Astrophysics Milestones for Pulsar Timing Array Gravitational Wave Detection. That's been led by Nihan Paul, myself, and the rest of NANOGrav as well. All right, so I think I'm almost out of time, but I just want to leave with a few minutes of what I think are the prospects for multi-messenger astronomy in this PTA band. Unlike LIGO, we expect that the black holes we're looking at will be surrounded by quite a lot of gaseous material, forming interesting accretion disk structures. And the accretion disks and the geometry of those that surround our black holes could create periodic signatures in light curves when we look in optical time domain surveys or even IR time domain surveys. So that gives us a really great opportunity to perform multi-messenger astronomy because if there's periodicity in the electromagnetic light curves that are coming from double AGN like this, that we can match up with the gravitational wave signals that PTAs can measure, then we can splice those data streams together and get more precise characterizations of the binary systems. Was there a question?
Yeah, what is the time scale that you guys expect before you'll be able to do like, say, pointing analysis of detecting, I mean, not just detecting a single binary, but localizing it to a spot on the sky and being able to do a follow-up electromagnetic survey?
Yeah. So our pointing is going to be quite poor initially, hundreds of square degrees. That's for a blind gravitational wave detection. However, there are plenty of candidate binary AGN where we see periodicity in their light curves. We don't know that they're actually supermassive black hole binaries, but they exist, and we can follow up in the opposite sense with gravitational wave analyses. So in that sense, we've got lots of candidates for which the sky location is known exactly. We can look in our data and validate whether it's actually a binary or not. That actually leads on to what I'm talking about here, is that there are two possible avenues to the multi-messenger detection. The first is that we'll have broad sky localization, very poor pointing, and then we'll, within this volume that the PTAs identify, we can do host galaxy identification, provided we've got deep enough catalogs, and then photometric follow-up. The other is that we've got lots of binary candidates that exist already. Let's do targeted PTA validation of those. It could be possible that, I mean, it certainly is possible that PTA data is not sensitive enough yet, but by the end of this decade should be sensitive enough to rule out many of these candidates as being true binaries or not. I'm going to skip over a lot of this, but wanted to highlight that this is ongoing work, fusing these data streams together into a dual likelihood analysis being led by my postdoc, Dr. Maria Carisi. We expect that the complementary functional dependencies that these different gravitational wave and EM signatures have will help us collapse the parameter space very well, and multi-messenger analysis should characterize these binaries better. In the last minute or so, I just wanted to point out that I've got a couple of very talented undergraduate students that are working on outlier isolation analyses in these kinds of PTA searches in time series, and also in photometric data. And in a separate simulation project, Katie Sella is working on looking in the illustrious cosmological simulation and saying, what are the characteristics of the galaxies within that could host a PTA detectable binary? So trying to understand the demographics of galaxies that would host supermassive black hole binaries for PTAs. So I'll end there. Sorry, I'm just on time, but thank you very much.
All right, well, thank you very much. That was a great talk. So yeah, any more questions?
Yeah. Oh.
Go ahead, Jed.
So the signal, or the tentative signal that you guys have, it's really just these 5 frequency bins at the lowest end of your range. Could you say something about, are there systematics that you guys are worried about dominating those bins? You know, for example, like you already commented on the interstellar medium affecting one of them. Are there other systematics that you guys have talked about?
So we are exploring this. You know, we do see this common process only in the lowest 5 frequencies. However, that is in line with our expectations for the kind of background we're looking at. And it is supported by a large number of our quality pulsars. Chromatic effects like dispersion measure, we think we've got an understanding of those, and they shouldn't cause too many problems. We do these observations across multiple radio bands in order to ensure that we can isolate these radio frequency dependent noise processes from our gravitational wave signals. So we do think we're doing that very well. To cross-check and make sure that we are actually seeing what we think we might be seeing, we're hoping to cross-validate with other data sets in the IPTA. So this is purely in NANOGrav at the moment, but we've also performed some preliminary analyses in the IPTA data set, which is a fusion of lots of our data sets together, and that seems to be here as well. So we seem to be getting good signs that this is not a systematic in just one PTA, but is actually common across all of the PTA data sets.
So I have a couple of questions. So one, you showed the timeline for if there was a quadrupolar signal, how the sensitivity would increase and how it would settle down to the Helling and down. Have you by chance done a similar analysis for dipole signals as well, and how things scale for them?
Yeah, so that's shown a little bit in this plot here in the top right. So if we did have a gravitational wave signal, if we did have a dipole signal, and we were trying to fit that with a Hellings and Downs template, then sure, the significance would increase over time. But the significance can only grow so quickly when you're applying the wrong template to the wrong process. And so that's shown in this purple region here, that's in between the monopole and the Hellings and Downs. So we have done a little bit of what you've mentioned, and we've seen that the true template, Hellings and Downs, will always win out. And at the moment, we are seeing that we're within expectations of where we should be for a Hellings and Downs correlate process. Now, of course, we have to couch our expectations in skepticism. This could be, could be a systematic we haven't thought of. For that, only time will tell, and working with our international partners will help to resolve this as well.
But suppose it was a new dipole process, a new dipole source of your signal, then I assume if you use the correct template to filter it, it will not grow as fast as Helling down because there is an inherent background coming from the solar system ephemeris, right? Is that correct? Yes,
right. But we do model out that dipole from the solar system. That's what the BaseFM model is essentially doing. It's doing it in a more physical fashion by actually modeling perturbations to the orbit of Jupiter and planetary masses, but it's effectively marginalizing over any dipole behavior in the cross correlations.
So to turn Jed's question around a bit, if this signal turned out not to be gravitational waves, what would you expect it to be? What would you sort of guess it was?
To be honest, that has me sort of scratching my head because it is quite a loud signal, but it is within the spread of predictions for the stochastic background. I think it's too loud to be a clock error, this global time standard drift that I mentioned. If we observe into the future and we do see strong evidence for Hellings and Downs correlations, then another question might be what other process can produce that very distinctive quadrupolar correlation signature? And that I don't know. I've thought of trying to make a bet with my colleagues, like $100 if they can concoct a signature from noise that looks like that. But I can't think of anything.
I mean, but at the moment, for example, like, I don't know whether this is possible, but let's say that these pulsars lived in environments where there were frequent gravitational perturbations to them, so they got moved around a bit. That would be something that would give you this kind of signal, but wouldn't give you a Helling Downs thing. Is that
right?
Kind of thing?
Yeah. So
I think astrophysically plausible. I don't know.
Yeah, common environmental effects would be an issue if these pulsars lived in the same cluster.
Oh no, but they don't have to be common. They just have to be statistically common, right? If the environments are such that with a common spectrum, they get moved around on such and such a time scale, then that's still enough.
Yes, yeah. So another possibility related to what you said is that there is there's something scalable and common about physics, the internal physics of neutron stars and pulsars that will produce this common spectrum red noise, common spectrum low frequency process. Yeah, so that is a concern, but given the the experts on internal neutron star physics within our collaboration don't seem to think that it could be a common signal from internal neutron star physics that's this loud. But we don't know. But we don't know.
But you would bet in favor of the quadrupolar signal coming along in 3-4 years' time.
I would say if it is a gravitational wave background, then in 3 years tops, we would have robust evidence.
Okay.
Cool. One related question, I don't know if you mentioned this already. Was there an expectation of when you would start seeing the stochastic gravitational wave background by some first principle calculation of what the amplitude should be?
Yeah, there was. So listed on the left here are some previous time to detection studies, and they all came in concordance with somewhere between 2020 and 2025. That's a big spread, but it's a spread over lots of different amplitude predictions. And of course, the higher the amplitude, the earlier you get there. 2026 is sort of reflecting if the amplitude is quite low due to biases in host galaxy black hole relationships. So if the black holes have to be lighter than we actually think, then the signal is going to be weaker, and so that will delay detection. But with an amplitude of 2 × 10⁻15, that puts us on the earlier side of this range, so closer to 2022, 2023.
Thank you.
So, as you take more data, like get longer time series, 2 things happen. One is you decrease the minimum frequency to which you're sensitive. And the second is for a given frequency bin, like the 3 nanohertz bin or something, you get more data and more significance in that one bin. Which one of those 2 things, if either one of them is dominating the increase in signal to noise that you guys are going to get over 10 extra years of data that you quote?
Yeah, that's a very good question. So as we go to lower frequencies, if the background continues to be this power law shape, then that's what's buying us the significance. It's the fact that the spectrum is very steep and increases as frequencies go lower. So that's buying us a lot of significance. The narrowing of the frequency bins means that we can resolve things better. And so it could be that as time goes on and our frequency resolution gets better, then our prospects for making single resolvable binary detections gets better. So it's easier for us to pick out these binaries on top of the background. And also, as we go deeper in frequency, hopefully we'll actually see a departure away from the power law so that we can start looking at this turnover behavior that's going to give us information about the dynamics of these systems in their final parsec of evolution.
And sorry, there is a first principles prediction for this power law. Is that true? Mm-hmm. And that it's roughly what you guys got. I think you probably said this. I just missed it.
Yes. So the prediction for a stochastic background of circular in-spiraling supermassive black hole binaries is just that it's a power law that scales as f to the -2/3. And what we found is that the amplitude, that the index was consistent with -2/3. But it's not, we don't have closed contours yet. It's consistent with even steeper spectral indices as well. So I didn't show it in these slides, but our posterior in the amplitude on the alpha value is quite broad, but consistent with -2/3.
And is there a time scale on which you will narrow that down to whatever? Well, I guess that's what I'm supposed to read off here, right? This is this delta alpha over alpha. So
yeah. So is rho hat of 25 is roughly what we would get for the full signal to noise ratio once the cross correlations are significant enough for us to have robust detection. And once they're at that stage, we would have an uncertainty of this spectral index of about 40%. And that's good enough to start discriminating the spectral index created by supermassive black hole binaries from some models of relic gravitational waves from inflation, cosmic strings, and other things.
Cool. Does anyone else have any other questions? All right, well, if not, then let's thank Stephen again.
Thank you very much.
Never
It was
know
a
what the
pleasure.
SK here is in
Thanks
this.
for the
But yeah, no,
invitation.
that was great. It's good to hear about, certainly feel like I understand what to look forward to a bit better now.
Yes, yes, it's exciting times. I'm looking forward to it, certainly.
Yeah, cool. All right, well, let's stop the recording.